Here we are going to study about the implicit function theorem. Implicit function theorem is a much more generalized idea. Now, suppose this y is basically a function of x1, x2, x4 and up to xn. This is basically an explicit function. Why is this an explicit function? Because here the dependent variable y can be completely expressed by the independent variable x1, x2, x3, x4 and up to xn. If we subtract the function of x1, x2, x3, x4 from y, then it becomes y minus function of x1, x2 up to xn equals to 0. So here we can say that capital F, that is basically you are assigning this entire part into a function. So this entire part is basically the function of y, x1, x2, x3 and up to xn. So we are assigning the entire part into a function, so that becomes function of y, x1, x2, x3 and up to xn, that becomes 0. So this number 2 equation, it is basically an implicit function of this number 1 equation. In the number 1 equation, you can represent the independent variables. In the number 1 equation, you can represent the dependent variables by the independent variables. I mean to say, you can represent the y, that is the dependent variable, by the independent variables that are the x1, x2 and up to xn. But in this function or in this equation, you can't represent y by x1, x2, x3 and up to xn. So the dependent variable y can't be represented by the independent variables x1, x2, x3 and up to xn. So in this function, this is basically becoming implicit. And because what is implicit? Implicit function is a function in which the dependent variable can't be explained by the independent variables. There is another video in which I have explained about the implicit and explicit function. Watch this video, then that will be very much clear, the topics. So this is basically an implicit function of the equation 1. We have derived this implicit function from the equation 1. Now, how to check implicity, that whether this function is implicit or not. So there are two conditions that must satisfy to be implicit, or for a function to become implicit, there are two conditions, two generalized conditions that must satisfy. First condition is that f. What is that capital F? That capital F is basically this f that we have assigned here. So this f, this is basically representing the entire function. So this entire function should have continuous partial derivative. That means we can do continuous partial derivatives of that function, and that must exist. So if we do the partial derivative of this entire function with respect to y, then what will we get? That is del f del y, then we are getting fy. So that is basically del f del y assigned as fy. Suppose it was del f del x, then we can easily say that it is fx. So it is basically nothing but assigning this del f del x as a part, or as a fx, as a name, basically storing it as a name. Del f del x1 become f1. You can write fx1 also if you want. Similarly, del f del x2 becomes f2. Now here what is important, that the first condition that we are actually talking about, that the function should have continuous partial derivatives. So we can see that f has continuous partial derivatives, because at first we are actually successful to do the derivative of the f with respect to y, then we are actually successful to do the derivative of f with respect to x1, again we are doing the derivative of f with respect to x2. So we are actually successful to do the continuous partial derivatives of the function or f. So the first condition is that the f has continuous partial derivatives, it is being ticked, and fy, f1, f2 should exist. We can easily see that fy is existing, f1 is existing and f2 is existing, but it should have a definite value. I mean to say, these are definite values that can be obtained. and fy should not be equal to 0. If fy is equal to 0, then the function can't be implicit. So for implicity, the f has to obtain continuous partial derivatives, and fy, f1, f2, both, all of those should exist. Even if we continue to do this by writing del f del x3, then we can actually see that it is becoming f3. So f1, f2, f3, all of this should exist, and fy should not be equal to 0. That means the partial derivative of the function with respect to the dependent variable, that is our y is nothing but our dependent variable. So the partial derivative of the function with respect to the dependent variable should be not equals to 0. This is the first condition of the implicity. What is the second condition of implicity? Now this is very important, that the second condition of implicity tries to tell us that function of y0, x10, x20, xn0 should be equal to 0. That means this x0, x10, y0, x20, xn0 are nothing but the neighborhood points. What are the neighborhood points? Well, neighborhood points are those points which actually doesn't satisfy the equation. So I am gonna make a detailed video on the neighborhood points, but if you plot the neighborhood points in the function, in the actual function, if you plot the neighborhood points that is denoted as y0, x10, x20 here, then it will give you a result of 0. That is the second condition of implicity or implicit function. I will make a numerical on the next video, and also I will make a numerical on the neighborhood points, and I will also make a numerical on how to determine the implicit function. So I will make this in the next video.